A Java collection is an object that does the job of a container by holding a group of objects for you. Most commonly, the objects are a group of data items that are related to one another, such as email addresses, phone numbers, or the cards of a solitaire game. Anytime you have a bunch of anything, you can keep that bunch in a collection. I'm using a collection to maintain the list of lessons that I'm recording for this VTC course. Java has a collections framework. It's a unified structure for maintaining lists. How many times have you gone through the process of writing and debugging a linked list? Have you ever gone to the trouble of building yourself a hash table and then discovered that you needed to have things sorted? The collections framework is designed to do all that work for you. The framework contains a number of interfaces that you can implement in your data items. They make it possible for a collection class to manage the data items for you. The framework contains a number of implementations that are capable of containing your data items and managing their organizations. They can do the sorting and searching for you. Once you have a collection, you need to be able to do things with it. The Java collection classes have algorithms that make it possible for you to do the things that you need to do. Probably the most common event with a collection is to sort it. It can be sorted in ascending or descending order. You can maintain a collection sorted in more than one way. For example, you could maintain a mailing list sorted by both name and by mailing date. The internal algorithm is a merge sort, which is fast and works well with both large and small lists. You can add new members to a collection, and you can remove members. A binary search algorithm can be used to locate one specific data item. Once you have a collection sorted, you can reverse the order of the sort with one simple command. You are able to duplicate all or part of a collection. You can overwrite part or all of every member of a collection with a specific value. You can change the order of two members of your collection. Shuffle is just the opposite of sorting. It will put your data items in random order. You can compare lists for being disjoint, that is, no common members. The next few lessons contain some collection example code. The next lesson looks into the general purpose collections. All collection classes implement the collection interface, or a sub-interface of the collection interface. Its definition begins this way. You can see that it uses a generic to specify the kind of objects it can hold. Oh, by the way, the objects held in a collection are called elements. You can also see that this interface is an extension of the iterable interface. I'll be talking about that here in a minute. Several methods are defined in this interface. In fact, a group of fundamental methods used in all collections can be found in the collections interface. Now, not all the methods are always implemented because for some collections, not all the methods make sense. But by using the interface and its standard method names, it's possible to pass elements from one type of collection to another. In fact, every collection class has two constructors. The default constructor, which has no arguments and simply builds an empty collection object, and another constructor that will accept any collection object as its argument. It builds a new collection holding all the elements found in the original collection. This makes it dead simple to transfer all of the elements from one type of organization to another. Anyway, the methods. These first two methods tell you about the contents. The size method returns the number of elements in the collection, and the isEmpty method returns true only if the collection is empty. The contains method returns true only if the specified element is in the collection. The add method inserts a single element into the collection only if it is not already there. The returned value is true only if the element was added. The bottom line, when this method returns, the element is in the collection. This method removes the specified element from the collection. The two array methods extract a list of elements and returns it to you as an array. I have some examples of doing this coming up. The iterator method encapsulates the elements of the collection in an iterator object, which can be used in a loop to extract the elements one at a time. There has been an addition to the Java language to facilitate doing this. The collection itself is an iterable object, which only means it can construct and return an iterator. Finally, there is a group of methods that operate on the entire collection. Contains all compares the contents of the two collections. Add all copies the contents of one collection to another. Retain all results in the collection containing only the elements found in both collections. Remove all removes the collection elements that are in the specified collection. Clear removes all elements. Almost all collections will have more methods than this, but this is enough to make certain that collections are compatible. Actually, some of these are optional in that they don't do anything for some collections. This interface has 10 sub-interfaces, and most collections implement one of those. As you saw earlier, the collections interface itself is a sub-interface of the iterable interface. All the iterable interface does is guarantee the presence of one method, the method that will return an iterator object. The interface defining an iterator object looks like this. It's set up so it can read sequentially through the collection one time. You have to call hasNext to determine whether there is another element to be read, and the next method then will return it to you. The remove element will remove an element from the underlying collection. In fact, it's the only safe way to modify a collection and continue to use the iterator. Using an iterator is straightforward enough, and it gives you control over your iteration. But some new syntax has been added to the Java language just for this special purpose. This special form of a for loop is for iterator objects only. The reference to an object named O is declared as a new variable. The body of the loop is executed once for each object in the collection with the reference O containing the address of the element from the list. It's just as though you had called the methods to get objects, except that you don't have access to the remove method. Also, this structure prevents you from looping through the contents of more than one collection at a time. A more general way to do it would be like this. This loop does the same thing using more traditional forms of Java. This gives you more control over what's going on. It also is a bit more clear and makes it possible to call the remove method. In the next lesson, a concrete example of using an existing general purpose collection. The original Java library contained a class named Vector. It was capable of containing any number of objects of any type. In effect, it was a variable length array. That class is no longer a part of the Java standard library, but it has been replaced by a class of the same name that requires generic syntax for its definition. It's very similar to the original vector class. It's a simple collection that keeps objects in the order you specify as you put them in. You can just append objects to the end of the list, or you can insert them in the middle somewhere. This example uses the vector collection class to hold a bunch of strings. It just appends them to the end of the array. By the way, notice that when you import a generic class with an import statement, you leave off the generic part of the name. But you must remember to do something generic when you create an object. Otherwise, it won't compile. In this example, the object class is used as the element, so it is possible to store any kind of object in the vector. This example just puts 5 strings into the vector container, then it reads the one with the index of 2, and then it displays it. Now, since this container was defined to contain any kind of object, it's necessary to cast the return value. When you run it, it looks like this. There you see that the index value of 2 reads the third string. It's a 0-based indexed array. Here is the same program again, but this time the vector was created to hold specific object types. In this example, you can see that the collection was limited to holding only strings. The rest of the code is the same, except, of course, the return value no longer needs to be cast. The get method was compiled to return a string object type. It runs the same as the other. As you can see, there's no difference. This is the same program again, but this time an iterator has been imported. An iterator is extracted from the vector and used to read through the members of the collection. The return value is a string, so it can be displayed in a print line statement. Here's how it runs. You can see that it returns and lists all elements of the collection. Now, I'm showing you this with a very small collection, but the vector class is capable of expanding to contain thousands of elements. One more vector, and the difference here is in the loop. The code to execute the loop is hidden. You don't have to have the iterator. Internally, this is exactly the same thing. An iterator object is used to index through the entire collection, but you no longer have to access it. You simply refer to the collection name for the loop, and it pulls out the iterator object and uses it. It stores the address of each element in the reference declared in the loop. In the next lesson, the set collections. General and special purpose, sorted and unsorted. This lesson is about sets. Sets are collections that contain no duplicate elements. Some sets can contain a null element. There are 2 fundamental kinds of sets. One kind of set is the special purpose set, and there are 2 of these. An enum set can be built to hold just enums of a special type. A copy-on-write array set does not store the objects you pass to it. It makes copies of the objects and stores the copies. But the sets you are probably more interested in are the general-purpose sets, and there are 3 of these. The hash set holds elements much like the vector collection does, but there is no ordering. The linked hash set is the same as the hash set, except it also keeps an order based on the order in which you add elements to it. It maintains a linked list that you can use to iterate through the elements in the order they were added to the set. In that regard, it is the same as the vector set. The tree set keeps the elements in order according to a key value. If sorted order is important to you, this may well be your choice. The simplest of the sets is the hash set. You can add things to it and retrieve things from it, just like you can with a vector. However, you should be aware that the elements returned through iteration are in random order. Here you see a hash set being constructed to hold strings. These 5 strings are put into it, and then an iteration is set up on it, and they are printed in the order that they are returned from the set. It looks like this. Notice the order. It is completely random. It is not affected by the order in which they were added to the collection. The linked hash set is actually a subset of the hash set, so it does everything the hash set does, and has the added feature that the elements iterate in order. This example is exactly like the last one, except for the name of the set. Here's what happens when it runs. The strings return through the iterator in the same order they were added to the set. So, this hash set is capable of doing everything the vector can do. There is a lot of conjecture about which is more efficient, but These considerations don't really come into play until you find yourself storing hundreds or thousands of elements. At that point, and if you have speed problems, you may want to try some different collections. It seems like every problem you try to solve is a little different, and the only way you can be sure is to experiment. Anyway, there is one more set to look at. This one keeps the elements organized in a tree. So it doesn't matter what order you put them in, the set puts them in an order for you. Here's what happens. At first, that might look like random order, but it's not. It's actually in alphabetical order. Well, sort of. It's in lexicographic order, which is another way of saying ASCII order. All the uppercase letters would come first, and some odd things like that. But you can write your own comparator and put them in whatever order you'd like. And that's the subject of the next lesson. Using different comparators with sorted sets puts the element in different orders. To be able to sort objects, it's necessary to be able to compare them. Now, the comparison results in a negative number to indicate less than, a positive number to indicate greater than, and 0 if they're equal. In the example in the previous lesson, the string object did that by comparing the ASCII characters. We are going to store objects of this class in a sorted collection. It's just a simple wrapper for a string name and a number. We're going to sort it first by one, then by the other. You can build one comparison method into the object and use it for sorting. Objects of the name tag class can compare themselves to others so they have a natural order. To do this inside a collection, it is necessary to implement the comparable interface. When they are placed in a sorted collection, the objects are cast to comparable objects and compared. This is the method that's called to do the comparison. This example just compares the name strings and ignores the numbers. Here is the construction of a tree set object that will be a container for name tag objects. It will hold them in a sorted order according to the compare-to method that we just looked at. Inside the collection, the name tag objects are cast to comparable objects, and the compare-to method is called to put them in order. The tree set has 5 name tags added to it in no particular order. Then an iteration loop is called to read them back and display them in whatever order they are being held internally. Here's how it runs. You can see that they were sorted according to their names. If you want to vary the order, you could change the compare-to method to sort them in any order you'd like. But there is another approach you can take. You can write an external comparator and use it instead of the internal comparison method. This class is used solely to make comparisons. It implements the comparator interface to be a comparator objects for name tag objects. It only has the one method. The compare method performs a comparison between 2 name tag objects. It does so by subtracting the numbers. The result is negative, positive, or 0, just what a collection needs to be able to put things in order. Using this new comparator on the constructor causes the tree set to use only the supplied comparator to put things in order. The rest of this example is just like the previous one. And here's how it runs. You can see that the names were completely ignored this time. The name tag objects came out of the collection in numeric order. In the next lesson, we're going to do a little more than just iterate in order. We're going to read by the key. Previously, we looked at the 3 general-purpose sets, and you saw how they sort their contents by keys. Well, there are 3 general-purpose maps. The maps work much the same way as the sets, except they have the added feature that they allow you to find elements based on a key. The names of the 3 map collections are analogous to the names of the 3 set collections. They even work very much like sets, but they do have some differences. It's that key thing. Being able to store and retrieve values by a key make things a bit different. The fundamentals are the same, but the interface is a bit different. Let me show you. This is an example that uses the first of the 3, the hash map. The class definition of the hash map requires that you specify 2 types, the key and the value that you are actually storing. The key is separate from the value. The 2 are not in the same object as they were in sets. As you will see, all ordering and comparing is done on the key. The value just sort of tags along with it. Anyway, in this example, the key is defined as being an integer class type, and the value is a string. As you can see, the types don't have to relate to one another in any way. When you put a new entry in the map, you specify both the key and the value. In this example, 6 strings are inserted as values, and each one has an integer for a key. The integers must be unique. If you try to insert a duplicate key, it won't work. The original value will be replaced by the new value. This loop iterates through the keys and prints the values associated with each of them. The values method returns a simple collection containing only the values in the same order they appear in the map. And the for loop then extracts an iterator from that. The iterator places the value of the elements, the strings, in the string object, 1 for each time through the loop. The result is that the values are printed in the order in which the keys are stored in the map. Now this second loop iterates through the numeric values of the keys and displays the string for each one. So we have 2 loops. The first one reports in stored order, and the second one in key value order. Here's how it looks. The first loop outputs the values in completely random order. That is to be expected because this is a hash map, and the keys are stored according to their hash values, which for all practical purposes is completely random. The second loop uses the key values in order to read the values. So it's output in key order. Now this is a version of the same program but with a different type of map. This is a linked hash map, which means the keys are maintained in the order in which they are added to the collection. The same 2 loops are executed. The first one will reflect the order in which the keys are stored internally, and the second one will be in order according to the values of the keys. Now, here's how it looks. The first list is returned in linked order, that is, the order in which they were added to the collection, and the second list is again in the order of the value of the keys. This third example is the same program yet again, using a tree map collection. Exactly the same code is used to retrieve the values, first in internal order and second in the order of the key values. Here's the result. This time the 2 lists are in the same order because the internal order is also the numeric order of the keys. There are a number of other things you can do with ordering in maps. With a tree map, you can extract values for a range of keys, and you can quickly get the first and last keys. You can even specify your own comparator on the constructor, like you saw in the earlier lesson with tree sets, and it will be used instead of the default order. The next lesson is about queues and some destructive read operations. A queue is a collection that returns elements to your program in a special way. You add elements to the queue in the normal way. The queue collection keeps them in some kind of predefined order, and when one is returned to you, it is also removed from the collection. All queues have at least two methods to insert a new element onto the end of the queue. The add method inserts the element and throws an exception if it can't. The offer method does the same thing, but instead of throwing an exception, it returns an error code. At least two methods can be used to return an element from the head of the queue. The remove method throws an exception if there is an error, and the poll method returns an error code. Both of these are what is known as destructive readers. That is, they do two things. They return the element and delete it from the collection. These two methods are non-destructive reads. They return the next element, but leave it in the queue. The queue classes fall into two categories. There are some that are designed specifically to work well with multiple threads, and I'll be describing those in a future lesson. But there are three that are not thread safe, but work just fine in a single-threaded environment. The priority queue is probably the simplest of all queues. The elements are sorted by either their internal comparison method or by a comparator that you provide on the constructor. It will accept duplicate key values for the sorting. It returns elements from the queue in sorted order, but the iterator does not return them in order. The ArrayDQ class, in addition to the usual methods for a queue, also can be iterated and has a number of methods, making it possible for you to access the elements in about any order you'd like. Some of the read methods also delete elements from the collection, and some do not. In particular, it has a push method and a pop method, so it can be used as a LIFO buffer, last in, first out. Such a buffer is also known as a stack. This collection is maintained as a double-ended linked list internally. You can add to and remove from either end. You can even add elements to a point in the middle. It also has push and pop methods, so it can be used as a stack. This is an example of the use of a priority queue. The elements in a priority queue are sorted in the same way we saw in an earlier example. The elements either implement the comparable interface, or you can provide a comparator on the constructor. Also, with the priority queue, you can specify the initial capacity on the constructor. It doesn't matter because the capacity will expand automatically as necessary, but you can increase the efficiency if you happen to know how many elements you are going to put in the object. In this example, the priority queue is constructed to hold strings, and they're not added in any particular order. All this is just as we've seen before. The difference is in how the strings are retrieved from the collection. This while loop executes as long as there are elements remaining in the queue. The poll method is used to read the elements. This method returns the head, the first member of the queue, and also removes it from the queue. Each string element is printed as it's retrieved. The result is that the strings are printed in queue order, and the queue is left empty. Here's how it works. As you can see, the elements are returned to the program in sorted order. So in spite of its name, this is not really a queue. It's a sorted collection with a destructive read. This is an example of using an ArrayDQ collection. This class can be used as a queue or as a push-down stack. It does not sort the elements. The order they come out depends on the order in which they go in. If you want to use it as a stack, which is first in, last out, you can use the method push to add the elements and pop to retrieve them. This example uses it as a queue, first in, first out, by using the methods add and poll. The body of this example is exactly like the last one. 6 strings are inserted in no particular order, and the poll method is used to retrieve them until the queue is empty. Here's what it looks like. There you see the result of storing a stream of elements in a FIFO queue. They come back in the same order in which they went in. You can continuously add and remove elements, and the queue will keep them all marching in single file, and give them back to you in order. The queue will grow to whatever size is necessary to hold all the elements that you give it. This example uses the linked list collection. It works the same as the previous example. The only difference is the internal implementation. In the previous example, the ArrayDQ used an array for internal storage. In this example, the linked list collection uses a linked list structure to do the same job. It can be used as a queue or as a stack. This example is just like the last one, and it works the same way. The elements come out in the same order they go in. Next up is copying elements from one collection to another and extracting arrays of elements. So far, we've looked at ways of pulling the contents out of collections one element at a time, but there are ways to retrieve bunches of elements at once. For example, there are two methods you can use to place the members of a collection into an array. This example is a program using a tree set to contain a collection of strings, just like we've done before. But the difference is how we take the strings out of the collection. This toArray method returns the strings as an array of objects. The size of the array it allocates is the same as the number of elements stored in the collection. In this case, the elements are all strings, but the method returns objects, so it's necessary to cast them to the right type before you can use them. This loop displays the entire array. Here's how it runs. You can see that the elements return in sorted order, the same order they return from the iterator of the collection. The size of the array is set to fit exactly the number of elements in the array. Let me show you another one. Here is the same thing again, but this example uses the other toArray method. To use this one, it is necessary to allocate an array of the proper type and size to hold the data. Using the new array as an argument on the toArray method instructs the collection to fill it up. Now, the type of array you pass to it follows the rules of polymorphism. Any type that the element can be cast to is fair game. Also, if you look at the Java documentation, you will see that this method also returns the array in case you ever happen to need that. The only advantage you get from all this is that you don't have to cast the elements before you use them. Here's what it looks like. There, you get all the elements in sorted order, as you would expect from a tree set. This example copies all the elements from a hash set into a tree set. This is the construction of a hash set to contain strings. 7 strings are inserted in no particular order. Of course, the hash set will put them in its own order. The strings are then printed in hash order, followed by a blank line. Then a new tree set collection is constructed using the hash set as an argument on the constructor. All collections accept other collections as arguments this way, but you'll need to check each one because most of them require other arguments on the constructor, things like capacity and the comparators. Finally, the contents of the tree set are printed, and here's how it runs. Here you see the output from the two collection iterators. The first is in hash order, virtually a random order, and the second is in the sorted order of a tree. In the next lesson, we'll take a look at using queues to pass data from one process to another. So far, the collections I've shown you are not thread safe. It usually doesn't matter, but if you're running a program with multiple threads, it can be handy to use a collection to share data. But you have to use special collections that are thread safe. The concurrent skip list map is a concurrent version of the tree map. The elements are in sorted order, and you can read an element on a key value. It even supports near key matches. The concurrent hash map stores items by key, but they are ordered only by the hash value. The queue collections are probably best suited to communicate from one thread to another. There are several queues that work in slightly different ways. The concurrent linked queue is a first-in, first-out queue that can grow to whatever size is needed to hold the elements you're sending from one thread to another. The sending thread can freely write to the queue, and the reading thread can try to read an element from it at any time. With the synchronous queue, a thread can only write to the queue if another thread is already trying to read from the queue. You can have multiple writers and multiple readers, but they will be synchronized by the queue. A blocking queue is one that blocks on reads. That is, when a thread attempts to read from an empty queue, the method doesn't return. The reading method blocks, waiting for an element to be written to the queue, and then returns it. There is more than one blocking queue. The only difference is the internal implementation. Let me show you how it works. This class constructs the queue and then starts the sending and receiving processes that send integer objects from one thread to the other. The queue is a linked blocking queue. The queue itself is passed to the sender and the receiver on the constructors, and both the sender and receiver threads are started. This is the sender, the class that puts integer elements into the queue. When it is created, it stores the queue locally for future use. The run method of the thread is a forever loop that continuously puts objects in the queue. It continuously creates new integer objects with the values 0 through 5. And it puts them in the queue. It has a sleep in the loop, so it sleeps for 2 seconds, that's 2,000 milliseconds, between each element that it puts in the queue. Now that's all the sender does. It displays the integer values and sends one integer every second forever. This is the receiver. It reads integers from the queue and displays their values. It's constructed very much like the sender, except it reads the values. It uses the poll method to do the reading. The method has a timeout on it. I just set that to 60 seconds so it wouldn't ever time out. The sender is putting one integer a second into the queue, so the receiver should always get one. The receiver displays the integer value. Then it sleeps the number of seconds of the integer value before continuing the loop. The sleep time varies from 0 to 5 seconds, so the two processes are never synchronized. Here's what happens when they run. At first, the sender is not writing as fast as the receiver is reading, so the receiver has to wait until an element is put into the queue. But the longer wait times of the receiver eventually take their toll, and the sender gets ahead. Integers start to back up inside the queue, and one is available every time the receiver loops around to read one. Two processes can be completely asynchronous and access the queue whenever it's convenient. That covers the basics of collections. A few other things can be done, but they're nothing more than variations on the things that I've shown you. Next, we're going to look into some deployment issues, some ways of getting class files to the users.